Hello, everyone. I'm a second-year PhD student in Paris Observatory, and I'm going to present you the beginning of my research. So I started my PhD by looking at the criteria, so I'm going to present this to you. And the goal of my PhD for now is to do a chaos map, so I'm going to explain what it is and the use for the Meteor community. So first, let's start with what are meteor showers. So we know what they are, but just I wanted to remind everybody that when I talk about meteor showers, I'm going to talk about meteors that come from the same meteorite stream and from the same parent body. The reason why I take the time to highlight this is because we sometimes have the tendency to use the words meteor shower to talk about several meteors sharing a similar radiant and having similar orbits. And well, we know that several meteors can share same orbits and still not come from the same parent body. It could be just a coincidence because of dynamics. So I will use the words meteor group to talk about those meteors that we as scientists have put together because they share similar orbits, but we do not know if they come from the same parent body. Sorry. So from this already, we can see that the next question we ask ourselves is, can we prove that several meteors sharing a similar orbit or a similar radiant come from the same parent body? And how can we prove this? So to answer that question, I took a look at all the papers that have been published to find and discover new meteor shower. And this is a method I found that most people use. So first, they try to look at the radiant of the different meteors. And then they compute the orbits and try to find if they're similar or not using the criteria. So, sorry. So this way you can create a meteor group and then you look for the parent body. We don't always find it because obviously a parent body could have been destroyed, but these are the first steps that most people do. Then some people also take it a little bit step further, which I think is very interesting. So we can, for example, take a look at a statistical analysis. So we have this group of meteors, right? And then we can try and see if, statistically speaking, this group could have happened just by chance or if it's actually significant. Another analysis we can do is an orbital dynamics analysis. So especially if we have an idea of the parent body, we just can follow it with dynamics and see if what we obtain is the same as what we see in our observations. And finally, when it's possible, we can also take a look at the physical properties of our meteors. So I'm thinking about age or composition when obviously those data are available. So here we can see that this whole interesting method is based on the very beginning, which is finding the radiant of the different meteors and trying to see how similar the orbits are. So I thought it was a good idea to take some time to analyze the criteria. So the first orbit dissimilarity criterion I could find in the literature is the one from Southern Hawkins, 1963, and this is a formula for small inclination. So when I discovered this criterion, I also found lots of articles criticizing it. So I'm going to make a small overview of the different critiques we can find because I think it's very interesting. So first, on the physical side, some also talk about long duration showers. So we talked about short duration showers in the previous talk. So here, if we take a look at the long duration showers, we know that the longitude of the ascending node is going to vary a lot from the beginning to the end, of the shower. So it's a little bit weird to have a criterion that's used to find meteor shower that use this specific quantity. Another critique that's been made is about the dimensions of the problem. So here we talk about meteorites, and we know for sure are going to cross the Earth's orbits. This is because they're meteors, right? So this means that we have only 4 dimensions in the orbit similarity problems, whereas the DSH here has 5 dimensions. Then we can take a look at the statistical side of things. So Southworth and Hawkins themselves did actually a statistical study on their own criterion. So they used several meteors and they did groups using their criterion. So basically they compared the different orbits of the meteors where all meteors share similar orbits. And then it took a look to see if those groups they formed could have just happened randomly or if they actually meant something. And they found that in about half of the time, those groups could have just happened by chance. They were just random groups and did not mean much more than that. And finally, I found some other articles talking about the units problem, which is pretty obvious when you look at the first two terms that I've circled. The first one is in eccentricity, so it has no dimension. And the second one is in the distance to the perihelion. So basically we have no dimension plus length square, which does not work. So I think, especially with these last two critiques, we can see that the DSH probably should not be used anymore. But that's okay, because we have lots of different criteria that we can find. A lot of people have proposed their own criterion, so that's very interesting. The only problem is that I could not find an extensive study that takes a look at each of those different criteria and see which one are more relevant. So if you know any of those study, I would be very interested in reading it. So I'm going to give you a little bit of an overview of those different criteria. Sorry. So the first two ones are actually modification of the DSH. They use the same kind of idea, and they just correct it for the units, for example, and try to make it a little bit better. This next one use observed elements. So for example, the observed velocity of the meteor from Earth. Then we have two more that use orbital variables. So for example, the energy of the orbit, or also the eccentricity vector, this kind of things. And finally, the last criteria use orbital elements again, but in a different fashion from the DSH. The reasoning behind it is completely different. There's many other criteria, but just this is a quick overview of the ones I could find. The only problem is that when I read the articles describing those very interesting criteria, they're not always a statistical or a dynamical analysis on each of them, which means it's not always easy to see which one we should use and in which cases. So I think from this point, we know that it's very complicated already to just make a consistent group of meteors. And so it's even more complicated then to find out which one come from which parent body. And if they actually come from the same parent body, are they actually a meteor shower? So the question I'm going to try to answer now is going to be a little bit different from the one I asked at the beginning of my talk. I'm going to try and answer, is it likely that a meteor group that we're interested in is actually a meteor shower? In other words, what probability can we give to a specific group of meteors sharing similar orbits? What is that probability that this group comes from the same parent body? So in order to add some new ideas to answer those questions, I decided to try and make a new tool for the meteor community, which is a chaos map. So as the name says, it's just a map of chaotic and stable regions, but I'm going to make it for meteorite streams. So this is to give you a little bit of an idea of what it looks like. So this specific chaos map has been made for satellite of Jupiter, so obviously very different dynamics, but it still is interesting to look at what it could look like in the end. So the idea is when you have the orbit of the object you're interested in, you can take a look at if it's stable or not. So in this map, and the dark purple part of the map, it's stable, and the yellowish part, it's more chaotic. So as you can see, it allows you to very quickly evaluate the stability of an orbit and follow the evolution of the meteorite stream. Now, this is a little bit abstract, so I'm going to try and give an example on how we can use it to answer those questions about meteor shower. Let's imagine that from Earth, we have noticed several meteors coming from the same region. Then we have computed their orbits. And with the appropriate D criteria, we have found out that actually those different orbits are very, very similar. So this is a very well-defined stream. Then we take a look at the chaos map and we say, okay, this orbit is actually in a very chaotic region. So we have a very well-defined stream in a very chaotic region. What does that tell us? Well, if this is a stream, a meteor shower, if it's actually coming from the same parent body, then it must be a young shower. Because if it was older, then it would have scattered everywhere because of the chaos. So we can look with other tools if it's actually that young. And if it is, then, okay, this is probably actually a meteor shower. And if other tools tell us that actually, no, it cannot be that young, then maybe we have to think that it's probably not a meteor shower. So as you can see, this reasoning uses a lot of different tools, so the radian, the D criteria, but we also should do statistical and dynamical analysis. The chaos map is not going to be enough to answer all those questions. And as you can also hear, I'm always going to talk about probabilities and statistics for this kind of resonance. Okay, so I hope I've convinced you that the chaos map is an interesting tool. Now I'm going to tell you how I'm going to try to make it. So first of all, how am I going to measure the chaos? Sorry. So I'm going to use an indicator we call the fast Lyapunov indicator. So the little problem with this indicator, it does not give you an absolute value. It's all relative. But that's all right because I'm making a map. So what I want to know is which which space, is more or less chaotic than the other. And this is something that the FLI will be able to tell me. Second thing is that the FLI is actually very interesting to follow the variations in time. So this is great because we want to know how meteorite streams are going to evolve. So we don't want to know if a space is going to be stable over 100 years. We also want to know if it's going to be stable for longer than that, and how is it going to be, is it going to become very chaotic, a little bit chaotic? So this is going to give very interesting results on all of those questions. Okay, so I'm going to show you my very first little result, which is this one. So I took 1,000 particles from the Geminids, and I plotted the FLI over 500 years. So you can see that at the beginning, the FLI climbed very quickly from 0 to the final value. This is just the computation of the FLI always does that. At the very beginning, there's kind of an initialization process. What's interesting is what happens afterwards. So you can see for all the Geminids, there's something very, very stable. The FLI does not change value, which means that Geminis over 500 years are in a very constant space, which is kind of expected from what we know with the Geminis. So yes, if you can see my mouse, you can see that there is several places where you have jumps in the FLI. So I figured out that this is because sometimes the Gemini cross have a close encounter with the Earth. So obviously when that happens, you have a jump in chaoticity, which is well seen in the FLI. So this little computation shows that the methods should work, and now I just have to make the chaos map. The challenges will be that the FLI is not typically used for non-gravitational forces. The FLI has been used several times, but always for gravitational forces only. So this is going to be what I'm going to try and make it happen for the chaos map, because we all know that meteorite streams obviously depend a lot on non-gravitational forces. So this is going to make the interpretation of the FLI results a little bit trickier, but that's fun in research, right? So in conclusion, I would like to remind everyone that, yes, when I talk about meteor group, I don't mean necessarily a meteor shower, because we can have several meteors just randomly being on the same orbit. The D criteria are wonderful and very interesting tools, but we have to use them critically because we have not been able to prove how well they work for every situation. If everything goes well, in a few years, I will be able to present to you my chaos map, which we'll be able to use in our search for meteor showers. And the goal of our tool is to evaluate the likeliness of a meteor shower. Thank you for listening. I would be happy to answer your questions.